Hello, welcome back. In the last lectures, we have discussed about finite difference approximations to elliptic equations, and in particular, we discussed Laplace equation, Poisson equation, and then arrived at system of equations. And we also discussed methods how to solve system of equations, because these systems need special attention, because these are sparse. Okay. So, now let us proceed further with various special structures, for example, derivative boundary conditions or polar coordinates, or when specific grid structure, how do we address elliptic PDEs and how do we discretize. Okay. So, to start with, let us make an attempt with the derivative boundary conditions. Of course, I would like to explain with reference to a specific example. So, the case 1 is like derivative boundary condition. So, this may not be so much different from what we have done for parabolic case, but nevertheless let us see. So, let us consider the example Okay, so, we have solved this subject to say u is 0 on x equals to 0 and x equals to 2, then u is 0 on y equals to 0, then dou u by dou y equals to minus u on y equals to 1. Okay. And say h is half. So, with this the grid becomes, so you remember x is 0 to 2 and y is 0 to 1. So, it is rectangular and h is half. So, the grid becomes so 0, half, 1, 3 by 2 and 2. So, this is the grid. Accordingly, so we have u is 0, then we have here u is 0 and u is 0 on this boundary. Okay. So, hence in a normal situation, when we have, let us say, Dirichlet data on the entire boundary, so then we would be knowing these points as well. However, since we have derivative boundary condition, so the unknowns, so we have to number them P 1, P 2, P 3. This also becomes unknown, okay, because here we have this is a mixed condition, okay, because this is Dirichlet and this is Neumann. So, it is in some sense this is a special case of alpha times u plus beta times dou u by dou y is prescribed. Okay. So, therefore, these are the unknowns. Okay. So, we have to find the solution at these points. So, let us approximate. So, the given equation so, now when we discretize, by h square plus 2 times u I j plus 1 by h square equals to 32. So, in the present case h is half. So, h square is, so we have in the denominator. So, in the numerator we get 4. Okay. So, we get the following, then we have minus 2, then we have minus 4. So, we have let us u I plus 1 j. So, then next one 2 times I j plus 1. So, I would like to write u I j plus 1, then u I minus 1 j, then 2 times, then we have minus 2 u j and minus 4. So, minus 6 u I j, and we have h square, that is 4. So, 4 takes it. So, h square. So, we get the right hand side. So, this will be 4. So, 8. Okay. I hope I am correct. So, let me check, because we have h square 1 over h square, that is 4. So, throughout 1 4 get cancelled. So, right hand side we get 8. Okay. So, now we have to discretize the boundary conditions. So, let us write down the equation again. So, now the boundary conditions, u of 0 y is 0. So, this implies u 0 j is 0, u of 2 y is 0. So, this implies u 4 j equals to 0, because the grid is x 0 equal to 0, half, 1, 3 by 2 and 2. So, this is 0, 1, 2, 3 and 4. Okay. Then we have, so this will be u I 0 equals to 0, and dou u by dou y at x 1 is minus u x 1. So, this implies, so more general if we do and then simplify, u I 3 minus u I 1 equals to minus half u I 2. Okay. So, this we can for example, if we do it more general case, u I j plus 1 j minus 1 by 2 h is minus u I j, and this is at x equals to 1. Okay. So, at y equals to 1, sorry, at y equals to 1. So, y equals to 1 in this direction. So, this is j equals to 1 and j equals to 2. Okay. So, I 3, because here this corresponds to y equals to 1, this corresponds to y equals to 0. So, therefore, from here we get. Okay. So, now let us write down the equations at each of the points. Which points? At each of the points we write down. Okay. So, we need the grid again. So, this time I am making a smaller one. So, 0, half, 1, 3 by 2 and 2. Okay. So, this is P 1, 2, 3, 4, 5, 6. Okay. So, j is 0, 1, j is 2 and I is 0, 1, 2, 3 and 4. So, therefore, the equation we have so, we have to write this equation at P 1. So, P 1, so this corresponds to I is 1 and j is 1. Okay. So, as I mentioned, we have to number them. So, we know these values. Okay. So, I am just marking. So, when we apply this at this point, we need this point, this point, this point and this point. So, accordingly I am writing u 2 plus, here it is u is 0, u is 0, u is 0. Okay. So, u 2 plus u this is 0, then 2 times u 4 plus this value is also 0, okay, minus 6 u 1 equals 8. Then at P 2, u 3 plus u 1 plus 2 times u 5, of course, this is 0 minus 6 u 2 is 8. Then P 3, so this is 0 u 2 plus 2 u 6 plus 0, then P 4. Okay. So, P 4 if we use, remember what we get. So, we need to introduce fictitious grid. Okay. So, since we have numbered like this, let us number this 7, 8, 9. Okay. So, this is fictitious. So, now at P 4 u 5 plus 0 plus 2 u 7 plus u 1 minus 6 u 4, then P 5 u 6 plus u 4 plus 2 times u 8 plus u 2 minus 6 u 5, and at point 6. So, this is 0 plus u 5 plus 2 times u 9 plus u 3 minus 6 u 6 equal to 8. So, remember we have these fictitious values. Okay. So, now these fictitious values we have to eliminate using the derivative boundary condition which we have So, the derivative boundary condition we have minus u at y equals to 1, okay, for all x. So, from here we discretized and we have obtained u I 3 minus u I 1, okay. So, we have to eliminate from here, okay. So, because when I is 1, so we have this is u 7, okay. So, let us put a remark, eliminate u 7, u 8, u 9 using star, okay. So, let us try this. So, if we do that, we have u 7 equals to u 1 minus half u 4, u 8 is u 2 minus half u 5, u 9 is. So, from where we have eliminated? We have eliminated from u I 3 from here, okay, and remember from here, okay. So, when for example, if I is 1, u 1 3, because j is 3. So, we are at the fictitious level already. With this notation, we are already at fictitious level, okay, with 3. So, therefore, when I is 1, it is 7, okay, and this is 1 1. So, that is u 1, okay, and 1 2. So, that is u 4, 1 2 is u 4, okay. So, similarly, when I is 2, 2 3. So, that will be 2 3. So, that is u 8, okay, and this will be u 2, okay. So, similarly, when I is 3, 3 will be u 9, okay. So, 3 will be u 9 and 3 1 will be u 3 and 3 2 will be u 6, okay. So, that is how we have got these fictitious values. Now, we have to use these fictitious values in this system, okay. So, we eliminate. So, let us do that. If we do that, we get u 2 plus 2 u 4 minus 6 u 1 is 8, then u 3 plus u 1 plus 2 u 5. So, these are nothing but the earlier equations. Sorry, this is 8. Then we have to start eliminating from the equation P 4. So, u 7, okay, and u 7 is this. So, we eliminate each one, okay. So, then simplify, okay. So, when we do that, we get u 5 plus u 1 minus 5 u 4 equals to 8, okay. Then next one will be, so let me do one of them. So, u 6 plus u 4 plus 2 u 8. So, 2 u 2 plus 2 u 8 and u 8 we have and minus 6 u 5 equals to 8. So, this gets simplified. So, this gets simplified u 6 plus u 4 plus 4 u 2 minus u 5. So, minus 7 u 5 equals to 8. Then the third equation. So, this is P 1, P 2, P 3, P 4, P 5, then P 6 u 5 plus 2 u 3 plus 2 u 9 minus 6 u 6. So, this will be simplified 4 u 3 then minus 7 u 6 equals to 8. So, there is some amount of simplification. Okay. So, then we get a system like this minus 6 1 0 2 okay. Then 1 0 1 and so you may verify this because this is just routine. So, I am putting it what I have obtained. So, we have this. Okay. So, this is a sparse system and one can solve and obtain. So, as you can see this is not so much different from the derivative boundary condition case which we have discussed in the parabolic PDE. Okay. So, all that we have done, we have eliminated the fictitious values by running the discretized equation and also by discretizing the corresponding boundary condition, derivative boundary condition. Okay. So, now let us see in case of polar coordinates how the corresponding discretization takes place. Okay. So, finite differences polar coordinates. Okay. So, consider Laplacian in r theta polar coordinates. So, this if we introduce okay. So, if we introduce then we have so, which means u is the dependent variable, r and theta are the independent variables. So, now definitely if we discretize Cartesian in this coordinate system, it is not going to help. So, we need to discretize the corresponding r theta plane. Okay. So, if you consider r theta plane, r as I h, maybe theta as j delta theta. So, we can call j k. Okay. So, where I is this and j is 0. So, what would be the corresponding discretization? The corresponding discretization could be so R is discretized 1, 2, 3. So, this corresponds to I 1. So, this corresponds to I 1, I 2, I 3, so on. Now, theta is also discretized. So, which means we have, so this will be, so this distance is corresponding to R. Okay. So, and this will be corresponding to theta. Okay. So, this is h, this is h, this is h, and whereas, so this is delta theta, this is delta theta, this is delta theta. Okay. So, we can number the grid points. So, for example, this point is 1 1. Okay. So, whereas this point is 2 1. Okay. Because this is on R 2 and J 1, right. So, I will be 2 here. Okay. So, we can number them. So, let us discretize the corresponding equation. So, now if we discretize the corresponding equation, we get, so the equation, let us write down the equation first. So, now if we discretize, plus 1 over I h, because R, then whenever we have first derivative, we go for central, then okay. So, this is our equation. So, this can be simplified further. If we simplify, let us collect, this is I plus 1 j and we have I plus 1 j and we have 2 h here. So, if we take h square common, 1 minus 1 by 2 I u I minus 1 j. So, u I minus 1 j first, then 1 plus 1 by 2 I u I plus 1 j, then minus 2 times 1 plus 1 by, so h square is cancelled, I delta theta square u I j plus these j plus 1 and j minus 1 terms, So, this is our discretized equation. This can be, so this corresponds to at each grid point. Okay. So, this can be expressed in the form of system where u bar is so on and so forth. Okay. So, this is n m and the matrix A So, this is just to know the structure. Okay. I am sorry, this is just to know the structure. I am sorry, this is a third row, I have to do it again. So, this will be so similarly we get so the matrix A would have this structure and the matrix B, each B 1, B 2, B 3. So, they also have a suitable structure. One plus so you can call B j. This is for the entire j delta theta square. So, we have a similar structure So, this is coming because of, so if we start writing at each of the grid points, we get, for example, if I equals to 1 and the j is 1, we get 1 1, 2 1, 3 1. Okay. So, these coefficients are sitting in the matrix B. Okay. So, they get multiplied with u 1 1, u 1 2, u 1 m. Okay. So, it is like that. So, this is just for a procedural sake. Okay. So, accordingly, if we take a specific problem, then we have to use the corresponding discretization. However, when you are programming, of course, you have to use these notations. Otherwise, like Cartesian, you get a simple system and one can solve. Okay. So, this is a general scenario with polar coordinates. Of course, I have not solved any problem. So, maybe if time permits we will see some specific problem involving polar coordinates. So, now let us see so far what we have discussed. We have discretized nicely, so that the domain is discretized in a regular grids, and we have discussed the solutions at each grid point. However, in these problems so far, the boundary is also been discretized, and some of the boundary points are also grid points. Okay. In case of derivative boundary conditions, and in case of Dirichlet conditions, straight away and the entire boundary is known. So, in that sense they are not some of them are grid points, but however, the entire boundary is known. But whereas, if you have derivative boundary conditions involved, so then even though we do not know the data, complete data, but we have obtained by discretizing the boundary, we have obtained the function values at those grid points. Now, suppose for a specific geometry, what would happen? Maybe the grid point is not coinciding with the boundary discretization. Okay. So, in that case, that means we have discretized the equation. Then when we demand maybe in the corresponding discretized formula, we are not getting the boundary points at all. Okay. So, then we have to take a special care. Okay. So, you will realize what I am speaking when I put it properly. Okay. So, let us proceed. So, this is more general case. So, this is more general case, which is called points of intersection of mesh lines and boundary of the domain are not nodal points. So, what do you mean? For example, suppose I take this domain. Okay. So, then when I discretize, so this is the domain. When we discretize, you see, so this is a nodal point. So, when we run the discretized standard formula, it asks these two values, these two values. Okay. So, points of intersection of mesh lines and the boundary of the domain are not nodal points. In this case, these are nodal points. Which are nodal points? Boundary points are also nodal points. Okay. Now, suppose we discretize. So, then what would happen? You can see clearly. So, this is a boundary point, but this is not a nodal point, because if we ask the discretized equation here, it expects these two values and these two values. So, this is not. So, this is the case where boundary points are not nodal points. So, we have to have special care. So, what is the care? If you see, suppose I magnify this. So, let us say, let us take this portion. So, then if you magnify, what kind of structure it is having? So, this is the structure, you can see. So, these this is giving a skewness, right. So, these two are skewed compared to these two, however, these two are equal and these two are equal. So, that means, if we start naming the size, this grid size is H 1, H 2, H 3 and this is H 4. Okay. So, this is more general, but however, in this case H 1 equals to H 3 and H 2 equals to H 4 in this case, but one can discuss a more general scenario. Okay. So, with this let us talk a more general Laplace equation, right. So, consider suppose we would like to approximate this, then say this is approximated by more general case, we are talking about more general case, right. So, identify point P 1 then point P 2 so this is H 1, then P 3 P 4 so means this is H 1, H 2, H 3, H 4. When I say these are these lengths. Okay. So, now we want to discretize this equation at these grid points. Okay. So, accordingly we have this must be approximated by alpha 0. So, this is so this stands, then alpha 1 so P 1 alpha 2 P 2 P 3 so this at x I y j we would like to approximate by this. So, now how do we determine the coefficients? Expand in Taylor series and collect the coefficients. We get, by doing so we get this is more general case where H 1, H 2, H 3, H 4 are different. So, we get this system. How do we get it? As I explained, you just have to discretize this. So, we want to fit like this. So, then you expand these in Taylor series and collect the coefficients of equal orders. That means, coefficient of u x I y j. So, for example, you can see coefficient of u x I y j. So, I will do coefficient of. So, from here alpha 0, alpha 1, four, and from here. So, this is minus f equal to 0 otherwise. Okay. So, similarly, we do it for other terms. Okay. So, now solution of star. So, solution of star is given below. Solution of star alpha 0, so for completeness I am writing. So, better you derive and then feel for it. Okay. This is alpha 0, quite big, alpha 1, alpha 2, alpha 3, So, this is a system, hence we have the corresponding finite difference approximation. However, if H 1 H, then H 2 H 4 is k. So, then the method becomes of order k square plus h square. Okay. So, this is one remark. So, otherwise we have general method. So, now let us see how this method can be applied to a typical situation. So, example, so we would like to solve Laplacian the circle. However, the first quadrant u is 2 on x is 0 and y is 0 and dou u by dou n which means, of course, this is a circle with the radius 1. However, we would like to solve the problem only in this, because of this restriction, and u is to x equal to 0, y equal to 0. So, here, but however, on this portion it is Neumann data on this. So, now as I explained earlier, if you discretize, we can discretize the entire one or only this portion. Say this is our portion, then if we discretize, then you have these points. So, you can see this arm and this arm of equal size and this arm and this arm of equal size. So, we have to obtain the solution. However, these points are not coinciding with the grid points. Of course, I have to draw a better one. This gives an impression that these are equal, but in a circle you can obviously see. So, how do we deal with this kind of So, let us have a look. So, what we do, so you can see this up to here, this would have been complete. So, the arms in this case H 1, H 2, H 3, H 4. So, in this case H 1 equals to H 2, H 3 equals to H 4, right. So, accordingly, the equation difference approximation becomes, for the Laplace case, if we compare Laplace case, which is u x x plus u y y equal to 0 with our original equation, a is 1. So, this suggests a is 1, c is 1 and d is 0, E is 0 and f is 0. So, with these things we get -2 So, u I plus 1 j plus 2 by j plus 2 plus 2 by So, when I say I plus 1, this is at H 1, j plus 2 means j plus H 2 and I minus H 3, j minus H 4, j plus 2 is u at x I y j plus h 2 u I j minus 4, so on so forth. So, the equation get simplified. Okay. But however, the challenge is when we approximate this, it will ask these points. So, we do not know, because this is not a grid point, okay, we have to pay special attention. Okay. So, when we solve the problem, we will see, otherwise this is the simple approximation, which on using h 1 equal to h 2, h 3 equal to h 4, further it gets simplified. Okay. So, this will this appears definitely interesting, however, we have to pay special attention, okay, because these are not coinciding with grid points, right. So, we will attempt this when we are solving a specific problem. Okay. So, this is a scenario when your nodal points and boundary points are not coinciding. Okay. So, when we solve specific problems, we will see how to handle. Okay. Until then, bye.